Chapter 2, Number 50. Jules Verne, in his novel From the Earth to the Moon, 1863, Verne describes a spaceship that is blasted out of a cannon called the Columbiad with a speed of 12,000 yards per second. The Columbiad is 900 feet long, but part of it is packed with explosives, so the spaceship accelerates over a distance of only 700 meters. Estimate the acceleration experienced by the occupants of the spaceship during launch. Give your answer in meters per second squared. Parenthetically, Verne realized that, quote, the travelers would encounter a violent recall, but he probably didn't know that people generally lose consciousness if they experience accelerations greater than about 7g, which is about 70 meters per second squared. And my instinct is that that is going to be way lower than what this spaceship has. So we need to draw a figure, and I've got some room over here on the right, so that's what I'm going to do. We have I'm going to draw it as a rocket, or the rocket part, or whatever, and we're going to say that the rocket goes over some distance I'm going to call, x, this is going to be x equals 0, and this is going to be x equals 700 feet, which is going to be annoying, but we'll convert and it'll be fine. And then we know that it picks up a velocity, which is 12,000 yards per second. So over here, v is 0, but over here, v is the 12 kiloyards per second. That's pretty badly drawn. My apologies. And in so doing, there is an unknown acceleration that we are looking for. Our key bit here is going to be to say that we don't have the time and we don't care about the time. We weren't asked about it, we weren't given it, so we'd rather avoid it. So we're going to go through an equation that looks like this, that v squared minus v0 squared is 2a times x minus x0. This is the more complicated and weirdest and last of the kinematic equations that we had. The derivation is online, it's a little strange, but its practicality is, its use is, whenever you have all the kinematic variables except time and you don't care about the time, then we've essentially solved the other equations for time once and for all, and we don't have to do it anymore. So looking over here, we can solve this thing over, and we can say that the acceleration is, reminding that, of course, this is 0 and that is 0, making life a lot easier. Our acceleration is just v squared over 2x, which is not so bad. And then they make the problem annoying because we have to actually do our conversions and so on. So we end up at 12,000 yards per second, and then we need to convert yards per second to meters per second, which means converting yards to meters. That number is virtually 1. There are 0.9144 meters in every yard. And then we square it. The seconds, like, happily is in, proper units of seconds, so yay for that. And then down here we have 2 times, and our distance traveled was 700 feet, and we'll need to convert feet to meters as well. And it turns out that there are 0.3048 meters per foot. Both of these things I just stole from Google, and you certainly would too. You're not really responsible for knowing British to metric unit conversions. So then we just can throw these guys into our calculator. We should be careful about making sure the square happens where it needs to happen, but we end up with 2821577 meters per second squared. This is approximately 300,000 g, which is considerably higher than the safe acceleration that makes people pass out. Actually, it's enough to probably turn them into jelly inside the rocket. This is not a good way to get to the moon. For really getting to the moon, we use rockets rather than explosives, because we can take a much greater distance over which you have to accelerate, and therefore the acceleration can be brought way down.